Hello, today's topic is internal forces, rectangular frames. I decided to solve one example for each video so that they don't last too long. So there will be another video with another example regarding rectangular frames. Therefore, you will learn today how to solve rectangular frames, how to write equations for internal forces for rectangular frames, and how to draw internal force diagrams. We have a rectangular frame, not among the easiest. Usually simpler examples are given at first, but in order not to consider an unknown number of examples here, I chose a more interesting one right away. We have a fixed hinge support, a movable hinge support. From above, it is loaded with a continuous load of 10 kN per meter, and there is also a pulling force P to the right of 10 kN. So the first thing we start with is the same as the dimensions 3x3. I will not rewrite them any further. There are 3 meters of vertical members and 3 meters of horizontal members. The first thing, just like with beams, is we need to calculate the reactions. I wrote them down as HA, Virginia, and VC. So the static equilibrium equations. Similarly to beams, it is best to start with the sum of moments. The best point to choose is point A, so the only unknown in this equation will be the reaction VC. So we have VC times 3 minus VC times 3 because it turns counterclockwise with respect to point A. And here, I calculated the resultant from the continuous load of 10 times 3 meters, which is 30. The resultant acts at the center of gravity, which is in the middle. And that is 30. So we have plus 10 because this resultant turns clockwise with respect to the line at A, clockwise. Plus 10 times 3, which is the resultant times 1.5 the arm of action, which is half of 3, and then also that 10. It turns clockwise, and its arm of action, which might be difficult to notice at first in frames, is such because I remind you what the arm of force action is. So what is a moment? A moment is force times arm, and the arm is the shortest, that is, perpendicular, distance from the direction of force action to the line of the moment. So the direction of force P action is as if we extended this force P. Its direction of action is exactly this dashed line, which may appear a little crooked, but you know what I mean. And the arm of action of this force P is the perpendicular distance from this line to point A. So this distance it's here, and its value is 3 meters. This is the arm of force P action. So it turns clockwise with respect to the line at A at an arm of 3, which means plus 10 times 3 equals 0. And from this, the reaction VC comes out to be 25 kN. From the sum of projections on the y-axis, Virginia minus 30 plus VC equals 0, Virginia equals 5 kN. And from the sum of projections on the x-axis, HA plus 10 equals 0, so HA equals minus 10, meaning I marked the direction of reaction HA incorrectly, so we cross it out, mark it in the opposite direction, and then we do plus and underline it to remember that we did this. Now that we have this done, it's time to write equations and draw graphs, so let's do that. We will make 2 cuts, conceptual cuts. One cut will start from the bottom and cut the frame, so we won't see the whole upper part at all. And the second cut will come in from the right side, so we will cut the frame there, and again we won't see what's to the left of our conceptual cut. As you remember from previous videos, we make cuts for our convenience, just like with beams. If it's convenient for us to cut twice from the left and once from the right, then we do it that way. Here it's convenient for us to cut once from the bottom and once from the right, so these cuts depend on convenience. We could do one from the bottom and then from the left, but in my opinion, it's easier as I've indicated. One of the problems that arise in frames can be the marking of forces, meaning that when we had a beam, we had specified signs for cross-sectional forces, normal forces, shear and positive moments on the left side, and we had them specified on the right side as well. But here, with the frame, There isn't really a left-right designation, but it starts from the bottom and the top. Then the question arises, where are the bottoms? And it can get a bit complicated, but let's get to the point. We have this cut here, which I drew x1 ranges from 0 to 3 meters, from 0 to 3 meters. Now we can visualize it, or turn the paper, and consider it as a piece, let's say, of a beam. So as if we were normally looking at a beam from the left side, meaning this is the simplest situation. The forces acting upwards. Torsional moments to the right are positive, and normal forces from the section. That's what I just mentioned. We can think of it this way, and on the right side as if we were dealing with a beam, meaning as it was in the video regarding beams, the markings are opposite. Positive shear forces point downwards, normal forces from the section, so opposite to here, and left torsional moments are positive moments. However, we kept in mind that at the bottom are the bottoms, meaning we didn't actually mention this at all, but that's usually not discussed regarding beams. This topic only comes up with frames. So this is my cross-section, and these are my markings, and the bottoms are on the right side of this, so that's the marking. I am aligning them as if I am rotating by 90 degrees and placing them here, like this. Exactly like this, so all right. So in that case, we can write equations. So my interval AB, point B, is here. x1 ranges from 0 to 3. Normal forces in this interval, meaning we already know that the positive direction is from the section, and the 5 is acting towards the section, so it's negative. There should be minus 5 here, I'm sorry. So this is minus 5 kN. The force, so it does not depend on the variable. There is no variable x1 here. In that case, for both 0 and the third meter of the beam, the force will be minus 5. Next, the shear forces. So we already know that our 10 is positive, which means that the wheel from x1 here has only that shear force of 10. Therefore, for both 0 and 3, the value will be 10 kN. Next, the moment from x1, which is that 10, because yes, 5, as we are calculating the moment in the section, so here. This 10 here directed, which means here. This 5 here directed along the beam does not create a moment, because it passes through the pole for which we are doing the sum. So only this 10, it rotates to the right, meaning that for us in this section it is positive at arm x1. And we check, for the values of 0 and for the values of 3 meters, we have 0.30 kN. Now let's move to the second section, so from the right side. It looks like this. So here it is, classic. A beam from the right side, there is no problem with the markings, so and so. We remember that there are supports here. I noted these reactions, 25 kN, and now we write the equations. So now our normal force is that 10. It acts from the section, in other words, it stretches our beam, so it is positive. Now, looking from the right side, here should be x2. It goes from 0 to 3 meters. Now we look from the right side, from 0 to 3 meters. The normal force is the positive 10, independent of the variable x2, so it is a constant value. The shear force, well, 25 in our section is negative, right? Positives are downwards when it comes to shear forces. So 25 is negative, and the resultant from the continuous load is positive. If you have a problem with the value of that resultant, I also recommend the earlier videos. This is particularly the first part of beams, which is 10 times x2. And it is at the center of gravity of that section, so if the section is of length x2, then the resultant is in the middle, or 1/2 x2. This will be needed for the moment soon, so we have minus 25 plus 10 times x2. Therefore, we have some dependent function of x2. Let's check. For a value of 0, it's minus 25, so we substitute 0 for x2. And for a value of 3, we have 5. Now we write the moment equation, which is 25 counterclockwise in this section. Positively at arm x, 2 minus 10 times x2, which is the resultant. The one I drew, and the arm of action of that resultant, is 1/2 x2. Now, sorting this out a bit, it is 25 x2 minus 5 x2 squared. Now let's check for the value of 0 and for the value of 3. For a value of 0, we have 0. For a value of 3, we have 30 kNm. And we can get started drawing the graphs. So we remember these values that we calculated, normal forces, so we get started on drawing the graph. We'll also talk about one more thing, how we will mark the graph, on which side there should be a positive sign. For example, when it comes to this vertical force, which side should be plus and which side should be minus. So we had accepted the underside inside the frame, so imagine you have such a beam, then the plus was always at the top and the minus at the bottom. So we will simply have for the graph of normal forces and for the graph of shear forces, minus on the side of the underside and plus on the opposite side of the underside. And I immediately note that this marking, when it comes to normal forces and shear forces, is not that important. I mean, you can draw the graph on the wrong side, but mark it correctly and there shouldn't be a problem with passing the exams. But when it comes to the moment graph, that is rather more rigorous and must be on the correct side of the graph. The moment graph is on the side of the tensile fibers. And we will assume, for example, when drawing the graph. And we will assume that if we have a positive moment, we will draw the graph on the side of the underside. So the positive graph for moments is on the side of the underside. Conversely, it can be assumed, like the opposite of the graph of normal and shear forces. Okay, I also copied this 15, it was 5. So our x1 is the vertical force, and here we have a constant value of minus 5. So on the side of the underside we draw minus 5, a constant value. And our x2 was the horizontal force. We have positive 10, so positive 10, the same value along the entire length. We mark the sign and value, and we have drawn the graph of normal forces. We move on to shear forces. We remember here what we calculated. I will write down the moments we calculated right away, because that will also be needed soon. So in that case, we prepare the area for drawing the shear forces graph. And we look at the vertical force, which is x1, a constant value of 10 kilonewtons. So positive, so I will draw positive 10 kilonewtons on the side, opposite to the underside. Now when we look at the horizontal force, we had for value 0, so our 0 was here. We have minus 25. On the other side, we have positive 5. And we connect it linearly because we were under continuous load. So here we have 5, here we have 25 minus. Well, we could have figured this out earlier, but here we can see that at this point on the moment diagram, there will be an extremum. Because under continuous load, the sign on the shear force diagram changes. From positive 5 to negative. The sign changes from positive to negative. There will be an extremum on the moment diagram, and this is the valuable information we need to extract from the shear force diagram. And now the question is, what is the distance from the beginning here, from the section where the extremum will be to the start of the beam? If we mark it as x, we can write that x minus 25 is like 3 minus x to 5. I talked about this in more detail in the previous videos. From this x we calculate. It is equal to 2.5, looking from the right side. In general, it's a distance of 2.5, so we had the moment equation written from the right side. So we substitute 2.5 into this equation and we find out what the maximum bending moment is in this interval. So Mmax from 2.5, I substitute here 2.5 and calculate that my maximum moment is 31.25 kNm. And I move on to drawing the moment diagram. So on the vertical beam, that is x1, we have a linear function. A linear function at the beginning, so here it is 0. And here we also note that at this point there will be x-rayum. At the beginning it is 0. At the end of this segment it is 30 kNm. And now it is positive, so it will be on the underside. Contrary to how it is on the shear force diagram and on the normal force diagram. One more thing. I say it this way. The diagram of moments is on the side of the tensile fibers. But this does not apply to the mechanical department, as I have rather encountered that in the mechanical department it is not done this way. But in most cases, in most departments, it is done this way. So we have the diagram on the side of the tensile fibers, and we marked this as positive. So we connect it linearly since it is a linear function, a positive value, and it is 30. And now here we will have the horizontal stress as a parabola. The value of the initial moment is 0. The value of the moment at the end of the interval is positive 30, so also at the bottom. And we have a maximum moment of 1.25 comma, so it's here. It's more than 30, so it's below this. And we connect this with a parabola. And we connect this with a parabola. 0, 31.25 comma, and 30. And the diagram is positive. Here it is 30, here it is 31.25. And we have drawn the internal force diagrams for the rectangular frame. If you have any questions about this solution, I encourage you to write in the comments below the video. Don't forget to subscribe to stay updated with materials from EduPanda. Best regards to you all. Bye!